SpatialAnalyzer is a powerful metrology software package for performing a wide variety of shipbuilding tasks while maintaining the high precision of today's most accurate measurement instruments. It is used for many shipbuilding applications, from aircraft carrier and submarine construction to ship component fabrication. SA supports over 100 different measurement instruments, from laser trackers and portable coordinate measurement arms to theodolites, total stations, and precision levels. It provides a single, unified interface for measurement, analysis, and reporting, which makes it easy to use for all steps in the metrology process. In this brief overview, we will demonstrate just a few of the capabilities of SA and how the software can be used to make ship construction more efficient and more accurate. SA supports a wide variety of file formats, allowing you to quickly bring in design data from other CAD packages, whether that data consists of simple points and lines or complex surfaces. With the new Apex import capability included in the SA plus native CAD package, just drag and drop the file into SA to import it. Adding an instrument is easy. Simply select Instrument, Add, and choose the desired instrument. In this case, we'll add a Leica total station. The instrument will be added to the job in a default location. We next start the instrument's interface directly in SA by opening the Theodolite Manager and adding our instrument of choice. It is worthy to note that there are options for saving instrument setups in order to make this process even faster. There are a variety of methods that can be used to locate the instrument into the ship's coordinate system. Among the many different choices, you can align directly to CAD surfaces, fit to nominal points, or measure a plane, line, and point in order to orient to an established reference system. It's common in shipbuilding to have a reference block defining a reference system for a given compartment or area of the ship. These blocks define the orientation of the reference system and also give a reference for a point in the coordinate system. One method to align to this reference is to use the plane line point instrument locating method. In order to use this method to properly locate the instrument in the ship's reference system, measure at least 3 points defining a plane, typically the horizontal plane in shipbuilding, at least 2 points along an axis, such as the longitudinal axis of the ship, and 1 point defining a point in the coordinate system. Then select Locate Plane Line Point. Once you choose the locating point, the points along an axis, and the points defining a plane, you will be presented with a dialog. In this dialog, you have full freedom to define how the measured points define the reference system. In this case, our top points define a horizontal plane at z equals 6.45 meters. The points on the side of the block define the x-axis of the ship, and the locator point is at 65.125 meters in x and 0.5165 meters in y. Note that you can look at the fit data before applying the fit. After clicking OK, the instrument will be located correctly relative to the reference block and further measurements can be started. Suppose that we now wish to locate an instrument into a previously measured reference system in order to take some additional measurements. This can be performed several ways, but we will illustrate a best fit locate. Assuming that a series of reference monuments had been measured earlier, the first task is to remeasure the monuments in the instrument's new position. Once at least 3 points are measured, we can now locate the instrument. This is a simple task of right-clicking on the instrument, choosing Locate, and choosing the best fit method. The user can look at detailed results of the fit and even exclude erroneous measurements. When the fit is accepted, the instrument will be located back into the same reference system and measurements can continue. SA keeps track of these operations in order to maintain a record of the measurement and analysis tasks that have been performed throughout the job. An instrument can easily be located to a new position by right-clicking and choosing Jump Instrument to New Location. This automatically creates a new instrument position and prepares it for additional measurements. Next, measure your tie-in points. Finally, locate the new instrument position and you are ready to begin measuring again. Another application in shipbuilding where SA shines is in alignment work. Consider an example in which we have a drive shaft that needs to be aligned to a nominal axis, shown here in green. Performing an alignment like this in SA is easy. We first measure the shaft in its starting position and locate a copy of our nominal model to the measured data. This has already been performed in this job. The current shaft location is colored red. We now construct relationships between the shaft's forward and aft centerline points and the nominal shaft's axis. Relationships are dynamic links between entities that keep track of the deviation between those entities. As the entities move, the deviation between the entities is automatically recalculated. We use these relationships to monitor the deviation of the shaft's current axis from its design position. We can also assign tolerances to these relationships, which automatically get highlighted to alert us to an out-of-tolerance condition. In this case, we'll set the tolerances to 1 mm radially. We can now pull up a relationship report, which will show us our deviations in real time. In order to track the movement of the shaft, we next measure a series of monuments that will serve as control points for our fit. We then make an adjustment to move the shaft toward its nominal location. After the adjustment, we remeasure the control points and fit the original points and model to the new location. Note that after the fit, our relationships update automatically. This process is then repeated until the shaft is located within tolerance. Watch windows are live instrument updates which allow you to align objects in real time. They compare an instrument's target position to any point or object of your choice. The windows allow you to attach tolerances to help guide the measurement technician toward an acceptable tolerance range. In this example, we've measured a pipe penetration through a bulkhead with a portable CMM. In just a few steps, we can fit a cylinder to these points, then check the orientation of the penetration against the nominal bulkhead orientation. Using relationships, you also have the ability to fit measured points to a CAD model. This can be used to locate an instrument or to locate a model to measured points. You have a number of powerful options, including the ability to constrain degrees of freedom during the fit and easily view the deviations of the measured points from the nominal model. SA is the only software of its kind that provides detailed uncertainty information for measured points based on the characteristics of the instruments measuring the points. USMN is a statistical analysis tool unique to SpatialAnalyzer that gives you the power to leverage the measurement characteristics of different instruments in a network to improve the accuracy of your measurements and calculate your resulting points uncertainties. This high-level demonstration has only scratched the surface of the measurement, analysis, and reporting capabilities available in SpatialAnalyzer. For more information, visit our website at www.kinematics.com or call us at 1-757-565-1500.